see the slides?
Yes, but the slides are okay, sir.
Okay, so good afternoon. Sorry. So ngayong hapon, pag-usapan natin ang building vibration and ground motion. Ito ang magiging outline ng aking presentation. So maikling panimula tungkol sa building vibration in general. Then vibration properties of structures, buildings. Pagkatapos ay i-iyata naman natin ang properties of ground motion, mga factors na nakaka-apekto sa ground motion or sa earthquake. And then structural response to earthquake, kung paano nag-behave yung ating structure sa earthquake. At finally, conclusion and recommendations. Building vibration. May iba-ibang sanhi or dahilan kung bakit umuuga or yumayanig ang ating mga building. Unang-una, halimbawa ay ang human activity. Madalas, kung nasa mall tayo or kung minsan napapansin natin na parang umuuga yung ating kinakatayuan o yung building. Specifically yung flooring, particularly kung halimbawa medyo mahaba yung span nung building, nung beams. Pwede rin ang vibration ay magaling sa mechanical equipment, like kung may generator set, so may mga compressor, nagpo-cause din yun ng vibration. And pangatlo, galing din sa environment. Halimbawa, mayroon tayong gusali sa tabi ng release ng tren. So pag nagdadaan yung tren, maaaring nararamdaman natin yung yanig ng gusali ng building. Maaari din na kung nasa malapit tayo sa kalsada, kung mayroong mga dumadaan na malalaking truck, pwede rin mag-vibrate yung ating gusali. Yung dalawang kadahilanan or sanhi ng building vibration, ayun yung mas particular tayo pag didesign natin ng mga gusali. Yung strong winds, malalakas na hangin, bagyo, or pagginig ng lupa or lindol. Ngayon, ano naman ang mga factors na nakakaapekto sa building vibration? First, may dalawang sanhi or factors na nakakaapekto sa building vibration. Una, yung structural vibration properties, yung vibration property ng struktura mismo. At pangalawa, yung ground motion properties. So sabi nga, it takes two to tango. So depende yon sa properties ng struktura at dun sa properties ng sanhi ng paggalaw. So tingnan naman natin ang mga modes of vibration and structure. Ang struktura, mataas na gusali, halimbawa, ay maaring mag-vibrate in different modes. So meron tayong tinatawag na primary mode. So yung first mode, pwede ring ito ay vibration. Ang isang example nito, kung meron tayong halimbawang water tank, so meron tayong overhead tank, pag nag-vibrate yon, essentially first mode vibration yon na yung meron tayong mass sa taas na gumagalaw siya, actually parang pendulum, baliktad na pendulum. So yun yung first mode of vibration. Meron din tayong second mode, so pagka medyo tumataas yung gusali natin, hindi lang yung first mode, pwedeng para bang may dalawang mass na gumagalaw, na nagpapalitan. So ito yung itsura pagka naggumagalaw siya sa second mode. Pwede rin na higher mode like the third mode na para bang may tatlong mass na gumagalaw ng independently. So yung pinaka mababa doon, yung fundamental mode or yung first mode ay tinatawag din natin na fundamental mode. Mapapansin niyo, maliban sa mga matataas na building, usually yung first mode ang pinaka-significant. Related sa period of vibration ay yung frequency, no? Vibration frequency or frequency of vibration. Yun, ang frequency of vibration ay reciprocal lang ng the period, no? So frequency is simply 1/T. Meron din tayong ibang properties like damping ratio, pero sa lecture na ito, mas bigyan natin ng emphasis yung mode of or period of vibration. So, paano natin kinukuha ang period of vibration? So, kagaya ng nasabi ko kanina, yung single degree of freedom ay para lang siyang pendulum. Ma-recall ninyo sa high school physics, college physics, meron tayong pamamaraan ng pagkuha ng period of vibration or oscillation ng pendulum. So kung natatandaan niyo pa yung formula doon, we have T is equal to 2 pi over square root of L over G, where L is the length. No? So kahalintulad ng pag-compute ng period ng simple pendulum, sa single degree of freedom, ganun din yung forma ng equation. So period is equal to 2 pi over omega, where omega is square root of k over m. Sa equation, yung k ay yung stiffness ng structure at yung m ay yung mass noong structure. So ang period ay ng single degree of freedom or ng struktura ay depende sa mass o sa bigat at sa stiffness, no, ng struktura. So makukuha natin ang period of vibration ng isang ordinary structure na nagva-vibrate in single mode using this equation. Ngayon, kung titingnan natin itong formula na ito na omega is equal to square root of k over m, maisusulat natin siya sa form na k minus omega squared m equal to 0. No? So kung single degree of freedom yan, makukuha natin directly yung omega sa struktura. Ngayon, kung ito naman, ang struktura natin ay nagba-vibrate sa higher mode, merong higher mode, second mode, third mode, and so on, makukuha din natin yung frequency, oscillation frequency ng ating structure. Ang stiffness at ang mass nga lang sa ngayon ay magiging matrix na. So it would be in matrix form. So merong pamamaraan para makuha natin ang stiffness noong structure na binubuo ng ating mga poste, mga biga, at yung mga mass ng struktura natin. Pwede rin ma-simplify na yung mass ay kada floor, stiffness ay kada floor sa kung gusto nating ma-simplify. So merong pamamaraan para ma-compute natin ang period ng structure. So sa primary mode or fundamental mode of vibration, meron ding mga madaling pamamaraan para ma-compute yung period. So merong mga formula na ibinigay at applicable ito sa static analysis, no? So sa mga simpleng structure na nagba-vibrate predominantly in the primary mode, so makukompute natin yung period equal to C sub n, h n to the 3/4. So nasa code ito, no? So depende yon sa property or sa material na ginamit, kung steel ba yung struktura natin, kung konkreto, or kung ibang materials. Mapapansin nyo rin, so ito ay sa 2010-2015 National Structural Code. Kung babalikan natin yung lumang code, no? Merong 1988 code. So bakit ako bumabalik dito sa lumang code? Kung mapapansin niyo dito sa lumang code, meron pang ibinigay na mas simpleng formula sa pag-compute ng period. T is equal to 0.098n over square root of D. So yung hn ay yung height ng structure. So depende ang period of vibration sa height ng structure at inversely proportional to the square root of D, where D is yung dimension parallel to the direction of motion. Doon sa 1988 code din, ina-allow yung pag-estimate ng period equal to 0.1n. So ito yung dahilan kung bakit ko gustong ipakita yung 1988 na NSCP na a very simple formula to estimate yung period of vibration ay 0.1n. So halimbawa, ang struktura natin ay isang palapag lang, so yung period niya approximately ay 0.1 second. Kung 5-story, approximately 0.5 second. 10-story, approximately 1 second. So yun yung pinakamadaling pamamaraan ng pag-estimate ng period of vibration. Of course, hindi ito accurate, pero it would give us yung feel kung gaano ba more or less yung period of structure. Ngayon, ang vibration ng structure ay nakita natin sa naunang equations ay depende sa stiffness ng structure at sa mass. So halimbawa, may tatlong mass dito na magkakapareho dahil magkakaiba sila ng taas, magkakaiba ng stiffness yung mga struktura. So ito ay mas flexible kaysa dito, or ito ay mas stiff kaysa dito, ito ay mas stiff kaysa dito, or conversely, ito ay mas flexible kumpara dito at ito ay mas flexible kumpara dito. Ngayon, yung pag-vibrate nila ay magkakaiba depende ngayon doon sa force na mag-excite ng vibration nila. Hindi ko na ipi-play itong video, but mayroong maraming video tungkol dito. Maaari niyong tingnan yung video tungkol dito kung paano mag-behave yung mga simplified structure na iba-iba yung stiffness. For this case, same yung mass. Pag binago-bago yung frequency ng pag-uga. So, kung bago yung ating dinidesign na struktura, madali nating ma-calculate yung stiffness, yung mass, kasi kontrolado natin yan, mababago natin yan. Pero paano naman kung halimbawa na existing na yung structure at unfortunately, halimbawa, hindi natin alam yung mga dimensions ng mga members, hindi natin alam kung gaano kalalaki yung columns, yung girders, and so on. Paano natin makukuha yung period of vibration structure? So, mayroon ding pamamaraan na makuha natin ang period of vibration ng mga struktura, na existing structure, sa pamamagitan ng tinatawag na Fourier analysis. So, ano itong Fourier analysis na to? Kung pwede tayong maglagay ng mga acceleograph sa gusali at mai-record yung acceleration. So yung acceleration record, pag nai-record natin yung acceleration, pag nai-record natin yung acceleration nung building, maaari natin siyang i-convert sa frequency domain using what's called a Fourier transformation. So, basta't makapaglagay tayo ng accelerogram, makuha natin yung accelerogram, maigagawa natin siya ng Fourier spectrum at makagawa tayo ng Fourier analysis. So, pag nasa Fourier, pag nasa frequency domain na siya, makikita natin yung predominant frequency noong struktura. Halimbawa dito, ito yung predominant frequency niya, at makukuha rin natin yung magnitude ng Fourier amplitude. No? So at may ganitong mga equation para ma-calculate natin yung Fourier amplitude. So ito ay isang particular na vibration ng isang part ng gusali. Ngayon, so kung isang gusali yan, pwede tayong makapag-record ng acceleration. Yung paggalaw nito, maaaring kung anumang salipa, maaaring magkaroon ng lindol habang at mayroon tayong instrumentation, maire-record natin yung acceleration. Pag i-convert natin yan sa frequency domain using Fourier transformation, lalabas yung mga predominant, or rather, yung mga frequency of oscillation or oscillation frequency. So halimbawa, sa example na ito ng isang 30-story building, nakuha yung mga frequency of vibration na 0.4 maximum, yung maximum siya at 0.4 cycles per second, 1.3 cycles per second, 2.4 cycles per second. So yung frequency na ito nagko-correspond sa 2.5 second, 0.77 second, at 0.42 second. So predominantly mag-vibrate siya at a period ng 2.5 seconds. So yung mga ito 30-story structure, approximately mga 2.5 seconds yung predominant period niya, no? For this particular example. Ngayon, tingnan naman natin ang properties ng ground motion. So, pwede tayong makapag-record ng acceleration ng earthquake using some instruments, strong motion acceleratograph. So we could record yung mga peak amplitude, yung maximum ground acceleration niya. Halimbawa, itong El Centro earthquake na i-record iyon. At ang peak ground acceleration niya ay lumalabas na mga 0.315 G. Yung Kobe earthquake naman ay nai-record din at lumalabas na yung peak ground acceleration niya ay about 0.8 G, no, in one of the directions. Makikita rin natin ang duration ng strong shaking. So, ikukumpara natin itong dalawang earthquake motion na to. Ito yung strong motion visually, no, mula dito hanggang dito yung lumalabas na strong motion phase. Dito naman, maliit yung PGA niya pero mas lumalabas na mas mahaba yung duration of strong shaking, no? So merong epekto itong mga ganitong properties ng ground motion sa behavior ng ating structure. Now, isa pang importanteng property ng ground motion ay yung frequency content. Sa next slide, i-discuss natin kung paano makuha yung frequency content. Also, yung general envelope shape. So, dito makikita natin yung envelope shape. So, parang pag ganun, dito yung malakas na motion niya and then nagte-taper off. Dito naman, medyo irregular ng konti. Malakas dito, then bumababa, lumakas muli ng konti, and so on. So, ito yung some of the properties ng ground motion na kailangan nating tingnan. So, paano natin makukuha yung frequency content? So, ito halimbawa ng isang earthquake din, maire-record natin yung acceleration and using the same method as earlier mentioned, pwede nating makuha or pwede tayong makagawa ng Fourier transformation at makuha yung Fourier spectrum. So, ito yung Fourier amplitude spectrum. And dito lumalabas na yung predominant frequency niya ay nasa around 2.5 cycles per second. So yung period niya is 1/2.5. So dito sa earthquake na to, predominant period niya is 1/2.5 o 1.4. Pero yung kanina example natin, lumalabas na yung predominant period niya ay nasa mga 2.5 seconds. So mas malayo yung uh, frequency content, no, yung predominant frequency content nitong earthquake na to dun sa previous na earthquake na nakita natin. Paano naman natin titingnan yung response ng structure sa earthquake? So, ma-measure natin yung response ng structure sa earthquake. Meron tayong tinatawag na acceleration response, velocity response, or displacement response. Ano itong acceleration response? So, kung meron tayong ground motion, i-apply natin yun sa ibaba, sa ilalim ng ating structure, gagalaw yung ating structure, at yung mass natin ay mag-a-accelerate. So, ma-measure natin yung acceleration ng mass natin sa input ground motion, at ito ang tinatawag na acceleration response. Ang pinakamataas na value na acceleration response, ito yung maximum response natin. Ngayon, ito ay sa isang particular na struktura na may given na period. No? Pag iba yung period ng structure, even for the same earthquake, may iba yung response, acceleration response, and mababago rin yung acceleration response. So, iba-iba ang inaasahan nating response ng structure depende sa period noong structure. Ngayon, kung pagsasama-samahin natin yung iba-ibang period ng structure, halimbawa, maximum response ng period ng 0.5 ay ito, 0.1 ay ito, 2.2 second ay ito, and so on. Ang i-graph natin ay yung tinatawag na response spectrum. So spectrum siya kasi spectrum for a period from a minimum of, say, theoretically 0, up maximum of 1 or 2 or 3. So sa spectrum na yon, makukuha natin yung maximum response. So yun ang tinatawag na response spectrum. So, note na itong response spectrum na ito ay particular sa isang earthquake. Pag mayroon tayong ibang earthquake, expectedly, mababago din yung response. So, paano natin gagawin yun? So, ito yung halimbawa. No? Different earthquakes would result in different response spectrum. Paano ngayon kung mag-design tayo? Kailangan ba na kumuha tayo ng acceleration record at kunin ba natin yung response sa bawat record na yon? Masyadong mabusisi yon sa mga ordinaryong structure or simpling structure. So, to simplify things, gumawa ng design spectrum. And another thing, hindi lang sa earthquake record nagbabago yung response, nakakaapekto rin or naapektuhan din yung response noong soil doon sa ilalim ng structure. So, apektado rin yung response natin noong type ng soil na kinakatayuan ng structure. So, para ma-simplify sa mga simpleng structure, ang NACP ay gumawa na ang tinatawag na design spectra. So ito ay nagsa-summarize noong mga response na naobserbahan sa iba-ibang earthquake, at ito ang pinagbabasihan natin ng design. So mapapansin nyo, ito ay function ng period. So kung magdi-design tayo, kailangan malaman natin ang period ng structure, at base dito sa period ng structure ay makukuha natin yung expected acceleration, maximum acceleration, and therefore, since force is equal to mass times the acceleration, makukuha natin yung forces doon sa ating struktura. So, ganun natin ma-design yung ating structure. Balikan naman natin yung ilan sa mga earthquake, yung frequency analysis. Halimbawa, yung Mexico earthquake. Ito ay kakaiba itong earthquake na ito. Ito ay nangyari sa Mexico City na mayroong lalim na 40 to 50 meters ng subsoil deposit. Itong earthquake na ito nangyari noong 1985. Magnitude 8.1, epicenter niya. Though ang epicenter niya ay 220 miles or 350 kilometers away from the epicenter. Ang PGA niya, peak ground acceleration, is only 0.168 G. Sa firm ground, 0.38. So, hindi ganun kalakas yung peak ground acceleration niya and napakalayo niya sa source sa epicenter ng earthquake. Another earthquake na nangyari dun sa same location ay yung Pentatlan earthquake of 1990. So tingnan natin yung pag-aaral na ginawa doon sa earthquake na yun. So ito yung earthquake record nung Pentatlan earthquake, and nung kinuha nila yung Fourier spectrum, lumalabas na yung predominant frequency niya ito sa earthquake na ito 2.0 second, 1.4, 0.7, and 0.5 seconds. So, ang predominant niya ay mga 1.4 to 2 seconds. Ito yung 2 seconds, ito yung 1.4 seconds. Ngayon, another example, before we go into that, another example naman ito ay yung Ecuador earthquake. This is the Mexico earthquake yung kanina na PGA is 0.168 G. Ito yung this is already the response spectrum. The period niya at 2 seconds taas yung response noong sa Mexico earthquake, and sa Ecuador earthquake sa 1.5 second naman yung lumalabas na pinakamataas na response na. So, ano ang nangyari dun sa Mexico earthquake? So, as a result of that, ang observation, mayroong 412 na multi-story building na nag-collapse, at karamihan sa mga nawasak na struktura ay from 8 to 18 stories. So, kung titingnan nyo, yung period niya, approximately mga 0.8, yung rough approximation, 0.8 to 1.8 seconds, which is malapit doon sa predominant frequency noong earthquake record. 324 buildings also ay seriously damaged. So, in conclusion, importante na malaman natin ang vibration characteristics, hindi lang ng struktura, pero pati ng potential na ground motion. Ang structural response na maaaring acceleration or proportional sa force, velocity, at displacement ay nagdedepende sa vibration properties of the structure as well as vibration properties na exciting force. Maaaring ito ay earthquake, at even sa wind, kailangan nating makonsidera yung vibration property ng structure. Vibration properties of ground motion are affected by such factors such as magnitude. Naapektuhan siya ng magnitude of earthquake. Mas malakas yung magnitude of earthquake, mapapansin natin mas matagal yung duration ng earthquake, like yung Mexico earthquake. Distance from the causative fault. Makikita natin na kahit malayo yung earthquake sa source, ay posible pa rin na malaki yung epekto niya sa mga structure, because kahit malayo, merong tinatawag na low frequency component. Yung mga low frequency component na yon ay hindi na filter out kahit malayo yung pinanggalingan ng earthquake. At for thick deposit of soil, kailangan natin na special consideration. Kailangan nating i-analyze ng mabuti yung soil, yung mga soil dynamic properties, at kailangan din nating i-analyze ng mabuti yung mga structure, particularly kung meron tayong mga matataas na gusali or mga non-regular na structures na itatayo. Ito. Maraming salamat po at sana ay nadagdagan kahit kaunti ang inyong kaalaman sa topic na ito.
Maraming salamat, Dr. Hernan, for your interesting, although a little complicated lecture. So, ang question and answers, Q&A natin, mamaya na siguro natin gagawin yan pagkatapos nung kay Dr. Jaime Hernandez, para sabay-sabay na lang, no? Isusunod na natin ang lecture ni Doc Jaime. Mamaya pag may question and answer na tayo, session, may konti tayong parang pampagana yata ang tawag doon, na may premyo na ibibigay sa mga lucky yung sino magtatanong may parang irarapol o pipili, no, kung sino yung mananalo ng token na prize, no. So magtanong po tayo para magkaroon ng magandang talakayan. Nga pala, no, ako si Jun Ignacio, isang professor din sa UP Diliman. Ang susunod po nating lecture ay manggagaling kay Dr. Jaime Hernandez, no. Si Dr. Jaime Hernandez Jr. ay nagtapos ng kanyang BSCE sa UP Diliman at ang kanyang Master of Science sa Saitama University sa Japan at ang kanyang PhD sa Civil Engineering ay sa University of Tokyo. Ang kanyang major ay tungkol sa structural health monitoring. Ito yung kanyang topic ngayon, no? Si Dr. Jaime ay naging head ng Structural Engineering Group ng Institute of Civil Engineering ng UP Diliman. Ang kanyang research interest, no, ay ito nga major niya yung structural health monitoring at saka wind engineering at saka disaster risk reduction management na napapanahon ang kanyang topic, no, ang kanyang expertise pala. Some of the significant projects na naging project leader si Dr. Hernandez ay ang development of a triaxial measurement system for vibration-based damage detection and its application to civil infrastructure in Metro Manila. Nagkamit po ito ng incentive award, PhD incentive award from the Office of the Vice Chancellor for Research and Development sa UP Diliman noong 2010. And in 2008 at saka 2010 yung duration ng project na yon. Meron din siyang isa pang project na siya yung leader. Ito ay tungkol sa development of wireless sensor network for vibration-based damage detection and its application to civil infrastructure in Metro Manila na nagkaroon din ng PhD incentive award noong 2010-2011. Si Dr. Hernandez din ay senior project staff ng Enhanced Severe Wind Vulnerability Curves of Key Building Types in the Philippines na sponsored ng DOST, no, noong 2019 up to 2021. So without further ado, let us hear it from Dr. Jaime Hernandez to talk about yung topic niya na structural health monitoring. Okay.
Good afternoon, everyone. Can you hear me?
Yes, we can hear you.
Okay. Tawag dito. Sa sobrang hirap ng tinuro ni Dr. Hermar, I was thinking I was just going to play a ukulele for you guys. baka by doing this mawala yung yung tawag dito, yung pagod at hirap sa pag-intindi sa lecture ni Dr. Hermar. Kasi yung lecture ni Dr. Hermar, pang graduate course yun. Talagang kailangan talaga maintindihan mo ng gusto. Okay. Bago ako magpunta doon sa aking lecture, okay, which is fundamentals of structural health monitoring. Itong ukulele na to, ukulele to ng anak ko. And I borrowed it kasi I just wanted to show some things first, no? Yung principle ng sounds. Okay. Kasi sounds and vibrations, ano yan eh, magkamag-anak yan, okay? Magkapatid, ano bang tawag yan? It's the same thing actually. No? So, okay. So for example, itong string sa taas, no, yung pinakataas na string nitong ukulele, okay? Pag okay, meron siyang tension force, okay? Because na-apply na tension force kasi hinihigpitan natin dito sa tuner, di ba? Kapag tinutune natin yung string, okay? Tapos, okay, meron siyang specific na length, okay? May haba siya, okay? Ngayon, kapag dahil dun sa length na yon na merong supports dito sa dulo, okay? Sa dulo-dulo, okay? Pag plinak ko siya, meron siyang particular na sound, di ba? Ganun ang sound niya, di ba? Okay? Ngayon, kung out of tune siya, note, I'm not an expert player, no, of a guitar or a ukulele, no? Hindi ako expert. Okay? So, I don't know if it's in tune or out of tune, no? So I'm sure marami sa inyo nakakaalam. So ako hindi ko alam. Pero yung anak ko alam niya. So, anong gagawin mo, 'di ba? Pagka siya ay out of tune, edi syempre, i-adjust mo dito sa tuner, 'di ba? I-adjust mo siya, ikutin mo, okay? Tapos checkin mo ulit yung sound. Di ba? So, gagawin mo yon hanggang sa makuha mo yung sound na gusto mo. Okay. Pero ano ba yung ginagawa mo? Okay? Effectively, okay, in engineering terms, di ba, ini-increase mo or dinidecrease mo yung tension force ng cable, di ba? Nitong string. Tama? Hanggang sa magbago yung sound. Tama? Yung tune. Ngayon, tingnan nyo. 'Di ba? May haba 'yan, 'di ba? Mula dito hanggang dito sa dulo. Ngayon kapag inipit ko dito, so dito na yung support sa sa may gitna, tapos i-pluck ko siya, nag-iba yung sound. 'Di ba? Ano sabihin nun? Ibig sabihin nun, yung sound na nakakreate ng string, okay, is dependent siya doon sa length ng string. 'Di ba? Kasi binago ko yung posisyon ng support eh. Dito na sa may gitna. Nag-iba yung tune. Pagka release ko, yan yung tune. Di ba? Yung ano niya. In the same way, kanina, pagka hinihigpitan mo dito sa tuner, nagbabago din yung tune. Di ba? Yung note. Okay? So ibig sabihin, yung note o yung sound o yung tune is also dependent on the tension on your string. Diba? Kaya ina-adjust mo to, iniikot mo to para matono siya, diba? Okay? So, yung mga bagay na yun, okay, gagamitin natin yan. Importante yun. I'm sure you understand about, if you're a guitarist or I don't know, violin player or ukulele, you'll be able to make the connection. So let me share my screen now. Okay. I hope you can see my screen. No? So this is fundamentals of structural health monitoring and sample applications. Okay. So okay, let's start. So well, that's a picture of a guitar, but pinakita ko sa inyo yung principles na gagamitin natin, okay, dito sa using a ukulele, no? So the first principle is sound is created because of the vibration, the back and forth or oscillatory movement of strings, no? So yung pag-pluck mo, tapos nagba-vibrate siya, no? Balik-balik. Okay, yun yung nagre-create ng sound. Okay? And yung pag-create, yung pagbalik-balik na yun, yung motion na yun yung vibration. Yun yung tinatawag na vibration, no? Back and forth. In this case, up and down, no? Or oscillatory ang tinatawag na motion, no? Ng string. That's sound, no? So, sound is created because of the vibration of the string. The string, okay, vibrates at a specific frequency. Okay. Kanina, kung nakikinig kayo, nakita nyo yung definition ni Sir Hermar about frequency. No? The frequency is 1 over the period of vibration. Okay. So, and kanina, sana na-pick up nyo din, the period of vibration is if you have an oscillating structure like a pendulum, okay, the period is the time it takes for one cycle of motion. The time it takes for one cycle of motion. Okay? That's a period. So that would be in seconds, no? Time kasi, no? Okay? So yung frequency is 1 over that, no? The time it takes 1 over the period. And so if you want a formal definition, the frequency is the number of cycles a pendulum or a structure or a string makes in 1 second. Okay? Ilang cycles yun ang frequency niya per second. Okay? So, ganun, no? So that's the one, no? The frequency defines the number of oscillations or vibrations per second. Tapos, adjusting the tuners kanina do sa ukulele, no? Adjusting the tuners changes the sound of the string. Thus, the tension applied on the string affects the sound of the string and its natural frequency of vibration, no? So, nagbabago yung string sound, yung sound from the string when you change the tension. And pinakita ko rin kanina, nagbabago yung sound kapag binago mo yung length. Okay? So yung tension doon sa cable or doon sa string affects the frequency of vibration. Kasi yung sound na yun na create is dependent on the frequency. Okay? So kung music lover ka, alam mo na pag mataas yung frequency, so yun, mataas ang pitch. Okay, nung sound, no? So mas maraming vibrations per second, ibig sabihin no? So take note of these things, no? So napakasimple lang from sound, okay, punta tayo sa vibration. Ngayon, okay, bago ko ipakita yung meat nung presentation ko. Okay, consider natin ngayon yung vibration ng taut string, no? Actually, pinakita ko na sa inyo yung principles using the ukulele, no? Now, let's say you have this string, okay, of mass per unit length m, tapos meron kang tension force na H on each end, no? Tapos yung length niya is equal to L. Okay? Now, you can see that pink kulay rosas na dot, no? Now, what we're going to do is we're going to follow that dot. Okay, yung motion niya, no? So, for example, I apply an initial displacement sa gitna, parang plinak ko. Tapos release ko lang. Ang mangyayari sa kanya, di ba? Magba-vibrate siya, di ba? So, taas, baba, taas, baba, taas, baba. Right? Ngayon, pag plinat mo yung position na yan, ng point na yan, over time. Okay? So, over time, horizontal axis mo over time, ang lalabas, ganyan. Okay? Take note, sinulat ko, assume no damping. Kasi alam natin na kapag plinak mo yung string, mas may damping, ang tawag is, magdi-dissipate yung motion, di ba? Mawawala siya slowly over time. So ito, walang damping. Na-assume natin yung ideal na case na walang damping. Kaya ganyan. Okay? Infinite. Okay? Infinite yung motion, walang attenuation ang tawag, no? Yung pag-decrease ng amplitude, attenuation. Walang attenuation ng signal. Okay? So yan yung kanyang magiging yung magiging graph. Okay? So yun yung displacement sa vertical axis, time naman yung sa horizontal axis. Okay? Ngayon, sabi ni ano yung period? Yung period is the time it takes for this to move from here to here to here and then back again. That's one oscillation. Okay? So ibig sabihin dito sa graph, from here paakyat, pababa, paakyat ulit hanggang dito sa dulo dito. That time is T sub 1. That's what we call in this case, okay, based on the fundamental shape, okay, yung shape ng vibration. That's what you call the fundamental period of vibration of the string. Okay? And ang formula niyan, may nag-solve na niyan and you can do some research. It's equal to 2L divided by the square root of H over M. Ano yung H? Yun yung tension force. Ano yung M? M is the mass per unit length. Ano yung L? L is the length of the string. Di ba sabi sa natin kanina, naapektuhan, di ba? Yung frequency, sabi natin, yung sound naapektuhan pag binabago mo yung tension force. Pag binabago mo yung L. Di ba? Which is exactly what is shown in this equation. Okay? Kasi yung fundamental period nga, di ba? Is equal to, sabi ni Sir Hermar kanina, 1 over F. So F is equal to 1 over T. That's the fundamental frequency of vibration in this case. No? Okay? Ngayon, so since the period is dependent on the physical properties of the string or the cable, a change in any of the physical properties of the cable will cause a change in the period of vibration. Okay? So kung binago ko si L, magbabago si T. Kung binago ko si H, magbabago yung period, magbabago din yung frequency as a consequence. No? So for example, binabago yung H, yung tension force, linusen ko yung sa ukulele, linusen ko yung tuner. Okay? Marireduce yung tension force, di ba? Pag na-reduce yung tension force, ang mangyayari, yung plot nito, time history ang tawag dyan, ulit, no? Magiging ganyan na. Okay, magbabago. Yung plot ng motion ng point na yon over time. Magbabago siya, nag-shift. You can see, no? Merong shifting. Okay? Yung nangyari, nag-lengthen actually, hindi shifting, no? Nag-lengthen yung period as a consequence. So, makikita mo, okay? Ito na nga siya ngayon, no? Hanggang dito na ang period, no? Okay? So kung kanina, mga 15 seconds, ngayon, mga 20 seconds na ang period. Something like that, no? Okay? Oh, not seconds, no? This should be like what? Milliseconds, no? Kasi that's a string, no? Mabilis lang yan, mabilis yan, no? So kung kanina, 15 milliseconds, ngayon, mga 20 milliseconds na. So, humaba yung period. Okay? So, kung nagbago yung properties na yun, nagbago yung tension, pwedeng na-loosen, for example, pwedeng yun, sabihin mo na na-damage yung string mo. Yung structure mo, na-damage, no? So, isasabi ko, pwedeng sabihin na yung blue, yung baseline natin, yung basis natin, yun yung undamaged. Yung pula, dahil nagbago yung tension force, yun yung damage na case. And so, using this, without measuring H, without measuring the tension force, nagkakaroon tayong idea, uy, teka muna, may damage. May damage sa structure. Okay? By simply measuring the vibration of the string. Okay? Ganun, no? So, yeah. So, F1, as I said, is the fundamental frequency. Okay? And if, sabi rin kanina ni Sir Hermar, no? If you plot yung tinatawag na, na plot ng frequency domain, no? From time to frequency domain using Fourier transform, okay? Makukuha mo isang peak lang na ganito, no? Magkakaroon ka ng isang peak na ganyan, which gives you the frequency of vibration, okay, of your string. Okay? So, ganyan ang magiging itsura. Okay? Ngayon, dapat mayroon pang isang peak dapat, no, on the right para dun sa pula, pero tawag dito, hindi ko na napakita, no? So example lang, just to show you na when you plot yung frequency in the frequency domain, magkakaroon ng peak. Tapos pag may peak, yun yung nagsasabi sa iyo na, okay, itong peak na to sa taas, yun yung nagsasabi kung anong frequency nung string, no? Nung frequency of vibration ng string. Okay? That's after you do a fast Fourier transform. Okay, sige. So, saan yung possible application nito? Di ba meron tayong cable supported bridge sa Metro Cebu, yung Marcelo Fernand Bridge, or there's this new bridge, di ba? Na tinatayo. Okay, na cable supported bridge din, cable stayed bridge. Okay? Ano yung possible na application? Monitoring of the condition of the bridge cables and their anchorage. Yung anchorage yung nandito, yung nagsusupport dun sa cable na yan. yung cables na yan, meron yung initial pretension, no? Na nag-hold dun sa deck. Kung mawala yung pretension na yon or lumina yon, may ding malaglag yung deck na yan and masisira yung structure. Okay? So damage to the anchorage, yung anchorage malusin, may result in a decrease in tension on the cables, which can be detected as a lowering of the natural frequency of vibration of the cable. Okay? So without being able to measure ano yung tension force, measurein lang natin yung vibration, kunin natin yung frequency, compare with yung frequency for a healthy structure. Okay? Kung mas mababa yung natural frequency, teka muna, baka may nangyari, may problema. Kailangan alamin natin. Kailangan natin i-check pa lalo in detail kung ano nangyari sa structure. Okay? So, ganun ang structural health monitoring. Okay? Ganun ang structural health monitoring. Okay. Introduction. Okay. So, ito yung outline of the presentation. Okay? Meron tinatawag na structural health monitoring framework, measurement of natural frequencies of vibration of Tatara Bridge, Hiroshima, Japan. Okay? Papakita ko sa inyo yan. Ginawa namin yan when I was there in Japan. No? Measurement of natural frequencies of vibration of columns of the ICE L1 and L2 building. That's a building in our in the campus. Okay, and of course, no, we did that for structural health monitoring, and then system identification using ambient vibration and finite element modeling of the UPD Carillon Tower. Okay, yung UPD Carillon Tower. No? And then finally, I'm going to summarize things. So this is the structural health monitoring framework, okay, by Son et al. Okay, there are 4. Okay, number 1 is the operational evaluation, where we ask the questions: why is monitoring needed, and also how is damage defined? Okay, so for example, for that string or for the cable in the bridge, damage would be a lessening of the tension force of the cable. That would be damage. No? Actually, pwede ngang hindi ka pa makakita ng cracks on the deck. Pero, na-damage na yung cable mo. So kung ma-detect mo yon beforehand, okay, before magkaroon ng cracks sa deck, masasave mo yung structure, di ba? Kasi maayos mo na bago lumaki yung problema. So, number 2, data acquisition and cleansing. What do we measure and how? No? So, maraming pwedeng i-measure, no? Hindi lang vibration, no? Mamaya pakita ko sa inyo in different ways of detecting damage. Number 3, feature extraction. What are the damage sensitive features? Yan tanong, no? Pagka sinasabing feature extraction. Ano yung damage sensitive feature? Yung diniscuss ko kanina sa inyo, yung frequency or period, yun yung damage sensitive feature. It's sensitive to for example nga, loosening of the anchorage and therefore the lessening of the tension force on the cable. Okay, yun yung damage sensitive feature. So if you can measure the frequency or the period of vibration, you'll be able to say, no, kung may nangyari sa structure or not. Number 4, damage detection and quantification. Ito na yung I think maraming tao na excited about, no? Kasi dito talaga hinahanap, okay, may damage ba? Okay, does damage exist? Nasaan location ng pinag-uusapan, no? Nasaan yung damage? Okay? What type of damage? Okay? And then gaano ka severe? How severe? Okay? Actually, meron pang iba na nagtatanong ng question na, okay, ano nang lifespan ng structure mo because of this damage? Okay? So, yun yung mga questions na tinatanong sa structural health monitoring. So, ang daming research na nangyayari when it comes to structural health monitoring. Kasi, okay, for example, sa data acquisition and cleansing, di ba, sa what do we measure and how ang tanong. Pero, yung question na, what do you use to measure the vibration, for example, is also a question, no? Ang daming different types of sensors that could be developed. Like kanina lang, in-explain ni Sir Jun, no, yung mga research na nagawa namin. Now, we've developed low-cost sensors, no, accelerometers to measure accelerations, vibrations, no, of different structures. Okay? Mapakita ko sa inyo mamaya yung ibang ginawa namin ng mga applications. So ito yung structural health monitoring framework, no? Okay, how do we know when a structure is damaged? Okay, there are 4 ways. Number 1 is visual inspection. That's normal. Everyone's doing that, no? Visual inspection using the unaided eye, using digital cameras, using video cameras, no? That's you can say all of those fall under visual inspection. Number 2 is sound or wave propagation techniques. Okay? Merong hammer test, may impact echo test, may pile integrity test. Okay? Yung pile integrity test, okay, you hit the top of the pile with a hammer, the wave goes down, and then yung wave na yon will be reflected back. The device on top will measure how much time it takes to go up. If the time it takes to go up again, the signal to go up again, okay, is shorter, that means there may have been a crack somewhere. Hindi nagtuloy hanggang sa baba yung signal mo. Okay? So, ganun, no, yung sound wave propagation techniques, no? So for file integrity test. Number 3 is the vibration-based methods. Tawag dito, which yung in-explain ko sa inyo, that's where it would fall, no? Where acceleration, velocity, or displacement of a structure is measured. From the vibration data, the dynamic characteristics of the structure are determined and compared with the undamaged case. So merong undamaged case, merong possible na damage case, no? So compare ninyo, if there are changes, then there may be damage, no? If the dynamic characteristics change, then the structure is damaged in the absence of other possible causes. Okay, that's very important, no? Kailangan kasi baka mamaya meron lang nagbago doon sa property because uminit yung panahon o nag-expand yung material, for example, no? So may mga ganun na cases, nagbabago yung properties as a consequence, hindi naman pala damage. Then number 4, non-vibration based methods using high-tech equipment. You could use X-ray, you can use infrared measurements, you can use radio frequency identification. Okay? So yung isang kasama namin sa civil engineering, si Dr. Antonio, nagre-research siya on mechanical devices that would go into damaged structures. Tapos maghahanap ng mga mga natabunan ng mga survivors. Alam mo iniisip nilang gamitin infrared. Makikita kasi yung heat yung heat signature, no? So kung makita mo yung heat signature, okay, kahit na natabunan, nandiyan sa loob ng tao, and therefore masasabi ng machine, dito ka magbungkal, dito ka maghanap. So maraming pwede, no? So pero tayo ngayon, dito tayo sa vibration-based methods, okay? For entire structure. Sinabi ko na sa inyo kanina to, yung different levels of damage detection, yung existence, location, how much is quantification, okay? What type of damage the cause, and again, yung prediction, no? Remaining life of the structure. Okay? Okay, ito yung mga example ng vibration sensors. You have the uniaxial accelerometer. Okay? Naglagay ako dyan ng picture ng peso para magkaroon lang kayo ng idea ng scale. No? So, ganyang kalaki siya. Okay? Ito, micro electromechanical systems, okay, accelerometer, or what we call the MEMS accelerometer. Take note, this is 100 micrometers. Maliit lang yan. Nandoon sa tip ng ng daliri mo. Okay, 100 micrometers lang yan. Maliit-liit yan. No? So that is actually being used even in your cell phones. Okay, 'di ba? Meron ng mga cell phones ngayon na nakaka-measure ng vibration. It's actually that's in there, no? In your device. And then meron tinatawag na laser Doppler vibrometer or LDV. Okay? Ito ang gold standard when it comes to measuring vibration. Okay? It's just there, I will show you a video. Okay? It's in the internet, no? So madali lang makita. Pakita ko sa inyo quickly. Oops. Nakita nyo na yung aking FB page. Nasaan na nga ba siya? Hindi ko makita. Sorry. Yeah. Okay. Ito. Sorry. There, this one. Nakikita nyo ba yung video?
No, sir. Nasa slide, sir.
Nasa slides pa rin. Okay, taga. I-stop share ko lang, ha? share ko yung yung video na yon. Saan siya? Ito. Okay, para magka-idea kayo nung laser vibrometer na yan. This is from Polytech, no? This is a company in Germany.
Laser vibrometry uses the Doppler effect to measure vibrations. If light is scattered from a moving object, its frequency is changed slightly. Within a Polytech vibrometer, a high-precision interferometer detects the minute frequency shifts of the backscattered laser light. To achieve this, the interferometer splits the light into two parts. The so-called reference beam is pointed directly to the photodetector, while the measurement beam is incident on the test object where the light is scattered by the moving surface. Depending on the velocity and displacement, the backscattered light is changed in frequency and phase. The characteristics of the motion are completely contained in the backscattered light. The superposition of this light with the reference beam creates a modulated detector output signal, revealing the Doppler shift in frequency. Signal processing and analysis provides the vibrational velocity and displacement to the test object.
Okay, so that is the principle, no? That is used in the laser Doppler vibrometer. And it's so high-tech, okay? This laser Doppler vibrometer is the one that is used by NASA, no? In monitoring yung mga structures in space, no? So, ganun ka high-tech siya. And tawag dito. Pero yun nga, sobrang mahal. Sobrang mahal. Okay, so you have different vibration sensors that you could use. No? Yung MEMS sensor, ang cost niyan mga 300 to 500 pesos lang yan. No? Yung LDV, magkano ba yung 15 million yen? Convert natin to peso, yun. No? Mga ganun ang presyo. At the time, no, that I was using the LDV when I was in Japan, no? Tawag dito, so I'm sure nagtaas na siguro yan by now. So that's very high technology, no, devices. Sige, yung uniaxial accelerometer yan mga 35,000 to 40,000 pesos a piece. Okay? So talagang yung low cost sensors, yung MEMS, yan yung best, ano? If you think about it. So okay, field measurement in Tatara Bridge, no, in Hiroshima. So this is conducted this in 2007 while I was there. 2006, 2007, okay. Tapos, okay, bale, ganito yung ano dyan, no? So, meron kaming LDV, Laser Doppler Vibrometer. Itong nasa taas nitong total station. I don't know if you're familiar with the total station. Okay. This is also an LDV, no? So, it's a single point laser, no? So, tapos, meron kang total station sa baba. Yung total station, yun ang ginagamit mo to be able to aim the laser, no? Kasi malayo yung distance. Pinag-uusapan natin if you are here, okay, on the road, tapos mini-measure mo yung vibration ng cable far away, mga 1 kilometer, 2 kilometers away, okay? Kailangan mo ng way para ma-aim effectively yung laser. Okay? So kaya pinagsama yung LDV plus total station like this, no? I-mount yung laser Doppler vibrometer doon sa taas. Ngayon, kapag in-aim mo yung laser, okay, up to a distance of mga 50 meters, okay, mangyayari, di ba, aim mo yung laser, mayroong babalik na signal, no? Mayroong mare-reflect na signal. Tapos yung reflected na signal na yun, na light, backscattered light na tawag kanina, yun at saka yung reference na beam, i-compare yun doon sa loob ng device. And doon malalaman ano yung changes, yung velocity nung structure, nung surface na mini-measure mo. Ay ganoon yung principle, di ba? Ang problema dito, sobrang layo, 1 kilometer, 2 kilometers away. Yung backscatter light mo, pag tumama na doon sa target mo, kukunti na lang. I mean, yung nag-scatter kasi yung light as you go further, di ba? Go further away. No? Try nyo yung flashlight. Kaya parang nawawala yung ilaw, di ba? kasi nag-scatter na, hindi ka na makita as a consequence. So, ang issue is, okay, anong gagawin natin? 50 meters lang pala yung kaya nitong LDV. Ang ginawa ng mga Japanese researchers, ginawa nila, naglagay sila ng prism in-attach nila sa cable. Okay? Anong ginagawa ng prism? Yung prism, di ba? Kumalat na yung light, di ba? Ang ginagawa ng prism, kino-collect niya yung light na yon, whatever light he can collect, and then yun yung binabalik niya as a concentrated light to the LDV. And therefore, the LDV is able to capture enough light to be able to make the comparison. Even at 1 kilometer away, even at 2 kilometers away. Ganon, no? So talagang non-contact ang tawag dito, non-contact health monitoring, structural health monitoring. So mini-measure yung vibration ng cables, no? So if you do that, no, you'll be able to excite lang nila, apply lang sila ng konting force, tapos magba-vibrate na yan. Measure nila yung vibration, and then they do the fast Fourier transform, and they will get something like this. No, ito yung frequencies of vibration of a cable. Now, you may be wondering, teka muna, bakit kanina isa lang? Ngayon, ang dami-daming peaks niyan, di ba? Okay. Kasi yung may tinatawag doon sa vibration ng... Okay, sorry. Isa na. Bakit hindi nag-work? Ayun, ang aking laser points. Okay. Meron tinatawag kasi kanina, ito yung mode of vibration kanina, di ba? Yan yung fundamental, yung F1, no? Yan yung fundamental frequency. Meron ibang frequency, ibang mode shapes and frequencies na nagba-vibrate din yung string, di ba? Meron parang nagiging dalawa, naglalaro kayo nung mayroong tansan sa gitna dati, I don't know. Anyway, so pwede nyo magawa yan, pwede yung meron kang 3 na vibration na ganyan, okay? So yung F2, yung frequency nitong mode shape na to or shape of vibration na to is twice F1 for a string. And so you can see, this is the fundamental, this is twice that. Okay, itong distance na to, no? So kung 0.5 ito, this is 0.25, okay? So tawag dito, kalahati. Tama ba yan? So mga 0.25 ito. So ito, meron kang frequency dito na 0.125. Okay? Mga 0.125 per second. And so if you're going to compute the period, yung buong cable na yon, mahabang cable na yon dun sa bridge, tawag dito, paano ba? Mahabang cable na yon sa bridge, ang period niya for the fundamental period, okay, the first period, yung T1, fundamental period, is around 8 seconds. It takes 8 seconds to make one cycle of vibration. Okay? Pero kasi yung vibration ng cable na yon, nung in-excite siya, ang daming iba-ibang modes na laman yung vibration na yon. Very complicated yung vibration niya, no? So, and etong lahat ng frequencies na to na-detect as a consequence. And again, it's just a multiple of F1, yung mga different peaks na yan. Okay? So that's Tatara Bridge in Hiroshima, no? O ito yung super remote sensing. Dali lang yan. Nando doon yung nasa kabilang island, yung laser Doppler vibrometer. Andi dito yung plate. Ito yung mini-measure niya. Ito, naglagay ng servo velocity meter that measures velocity as well. Tapos ito, accelerometer to measures acceleration. Anyway, tawag dito, to measure yung vibration nitong plate. Tapos yung LDV with the total station, nandun sa kabilang island, nagme-measure din ng vibration. Okay? Kasi ito yung comparison, no? So, yung first time, second time, third time, this is natural frequency using LDV plus total station. Ito, natural frequency using servo velocity meter. And they get exactly the same value. Which proves that that setup, the LDV with the total station and the prism, okay, at the back side of this thing, of this plate, is effective. Okay, so for super remote sensing. And that's, I think, around what? 2 kilometers, sabi niya, no? Around 2-kilometer distance. Okay? So, that's sa Tatara Bridge. No? Ito naman, yung ICE L1 and L2 buildings. Okay. Oh, ito, napakita na kanina ni Sir Hermar. No? Why the natural frequencies of vibration? Why do we want to, tawag dito, monitor natural frequencies of vibration? Naalala niyo to, di ba? Omega squared is equal to K over M. Hindi ko na didiscuss yan. For some, they're already familiar. Anyway, omega squared is equal to K over M. That's the natural frequency. Now, note that K is the stiffness. And what is the stiffness a function of? The stiffness of any member of a structure is dependent on the modulus of elasticity, E, the moment of inertia, I, the length of the member, the cross-section of the member, and even the mass per unit length. Yun yung K is a function of all of those properties. Okay? Tapos yung M, of course, is the mass of your structure or of your member. So anong ibig sabihin nun? Yung natural frequency is, okay, which is equal to K over M in this case, is an inherent property of the system. Okay? It does not change, okay? And it's not, it does not vary if you apply a different amount of force on your structure. Okay? Invariant ang tawag, no? So that's the natural frequency. Kaya yan ang monitor natin. Okay? Kasi pag may nagbago dyan, ibig sabihin, pwedeng nagbago si K, pwedeng nagbago si M. Kung nagbago si K, teka muna, baka nagbago si I. Si I is moment of inertia. So, baka nagkaroon ng cracks. Diba? Marireduce yung moment of inertia as a consequence. Okay? Things like this, no? So, yan yung reason. And we did this for UP, ICE, L1 and L2 building. This is the L1 and L2 building. It's a laboratory, It's a big laboratory. And what we did was we measured the natural frequencies of vibration of these columns on the sides over here, no? So, yan mga columns na yan. Yan yung measure yung natural frequency. So, in data acquisition, what we did was we used free vibration test on the columns. Okay. Ano yung free vibration? Bale, free vibration is you apply an impact force and then measure the vibration after the impact force. Yung free vibration, yun yung slowly nagde-decay. Okay, over time. That's the free vibration. It's not caused by any force. Okay? Yung structure lang slowly humihinto sa pag-vibrate, no? So that's the free vibration of your structure, no? Of your, in this case, the column. And then convert to frequency domain using fast Fourier transform, and then the peak-picking method, which is identify which is the peak to determine what is the natural frequency. Meron pang ibang methods, no, na ginagamit for data analysis. Ito, medyo high-tech to, no? Stochastic subspace identification technique. I won't explain that anymore, pero at least you have an idea that there are other methods na high-tech to be able to come up with the natural frequencies. And then a modeling was made, initial model from the design documents, and then the tuning of the model with the data, no? So that you have a tuned finite element model of your structure. So ito yung free vibration test procedure. Ito yung dalawang accelerometers. Yan, no? So 2 accelerometers, 3 trials were made. The sampling frequency, okay, bali amount of data that you're getting, no, recording, is 1,000 hertz, no? So 1,000 samples per second. Ganun kadami. Okay? So nakita nyo, ito yung computer connected to this device. This device converts the vibration to voltages. Tapos yung voltages na yun yung rine-record dito sa computer, no? Okay? So recorded siya. Okay? Tapos you just have a factor that you apply to convert the voltage to acceleration. Okay? Parang ganun. Now, you might be wondering, paano mo i-excite yung malaking column? Ito yon, yung susi dyan. Ito. Ano to? That is a wooden hammer. Siguro mga 8 to 10 kilos yung bigat niya, no? So itong si Carl, okay, when he was doing that, kita niyo, pawis na pawis siya, no? Kasi ilang beses siya nagpupukpok doon sa column para lang mag-vibrate yung mga yan at makuha niya yung natural frequency of vibration as a consequence. So ganyan yung approach. And ito yung typical free vibration time history. Ito yung pagtama nung hammer, no? Nung wooden hammer doon sa column, and you get tawag dito, tinanggal niya na yung impact, no? Impact dito, tinanggal niya na yung portion. Pero you get a free vibration graph that looks like this. Okay, di ba? Mabilis mawala, di ba? So, malakas ang dumping niya. Okay? So, ito yung inanalyze niya, no? So, dito naglagay ng zero padded data, okay, para mas smooth yung plot ng natural frequency, no? So, using this data over here as your input, time history input yan, convert mo to frequency domain, you will get something like this. And that peak over there identifies what your natural frequency of vibration is. So, if you look, it's around 150 hertz, no? Ganun kabilis. 150 cycles per second. Ganun kabilis yung vibration nung column mo. Kasi ang laki nga, massive siya. Okay? So, ganun ka talaga. So, that's using fast Fourier transform. Okay? So, ito, ginawa lahat, sample results for ppm for many of the columns. Okay? Tapos, ginawa niya din for the SSI method. Okay? Compare. Okay? Tapos, gumawa siya ng building model using SAP 2000. Okay? So, ito, nag-simulate siya knowing the properties of the members. Okay? He was able to simulate a model. And ito yung simulation results with comparison to SSI. So, ito yung SAP. Okay? Frequency na nakuha from the simulation. Yung percent difference comparing to the peak-picking method and the SSI, no? Ang baba. 6.58%, 6.6%, 1.4%. Okay, maliliit lang yan, 0.17%. Okay, which shows you just how effective the method is in coming up with the natural frequencies of actual structures in the field. No? Sige, so that's the other one. Ito yung local column mode shape at 140.4 Hz. No? Ito yung mode shape ng columns. Okay, na nakuha niya. So, next is yung system identification using ambient vibration and finite element modeling of the UPD carillon. Yung kanina, free vibration after mag-impact. Ito, ambient vibration. So, si Sir Hermar sabi kanina, ano may ambient vibration? Ambient vibration is vibration coming from the environment. It could be from people walking, running. It could be from machines. Okay? In the environment, okay? It could be from the wind, it could be anything, no? Ambient vibration ang tawag doon. So in this particular case, kasi pinag-uusapan natin is yung UPD Carillon Tower. I don't know if you've been here and you've seen that. Of course, okay? So wind, okay? Possible source of vibration, the ambient vibration could be wind, could be kung may construction somewhere in the vicinity, pwedeng maging source yun ng vibration, no? So, ito yung structure, ito yung finite element model na ginawa niya, no? And this is the location of the accelerometers. That's where we placed our accelerometer, no? So, bell tower, level 1, okay, bell control level. Merong control level doon, floor sa loob, okay? Meron din yung sa bell level, naglagay din ng accelerometers doon. And din dito sa level 4, level 3, no? Fourth, meron din yung accelerometers. Ito yung mga accelerometers na yun, you can see, no? Now, you may be wondering, teka muna, bakit ganyan ang arrangement ng accelerometers? Note that what tawag dito, Helimar did was, okay, naglagay siya ng uniaxial accelerometers perpendicular to each other to be able to measure, okay, yung acceleration or vibration in two mutually perpendicular directions. Okay? So, kaya ganyan. So, meron kaming plate na ginamit na doon in-attach yung accelerometers. In the same way here, here, and over here. Okay? So, and these are the ambient vibration acceleration time histories na nakuha niya. So, you can see, okay, ito yung raw data, ito yung detrended. Yung detrended, bali, basically, ang ginawa mo lang, inalis mo lang yung initial acceleration record, no? So, average mo lang yung mga yan, makukuha mo itong tinatawag na detrended. Kinuha mo lang yung average. And you can see, no, based on the time history, it's actually random vibrations. Kasi nga, ambient. Random talaga. Hindi katulad nung kanina. Nung kanina, free vibration. Very distinct. Ito, random. Now, the thing is, using these random vibrations, you will still be able to get the natural frequencies of vibration of the structure. Okay? Ibang method lang yung gagamitin mo. Okay? May ibang method. And ito, ang ginamit niya, yung tinatawag na next ERA. No? Next is natural excitation technique. ERA is Eigenvalue Realization Algorithm. Medyo medyo highfalutin. Okay. So i-research niyo kung gusto niyo maintindihan. Pero yun yung method na ginamit niya, no? And that is how he got the different natural frequencies, no, of the Carilion Tower. So 4.55 Hertz, 15.621 Hertz, okay? Itong Ma'am C or Mach, actually walang small m dati, no? Yung Mach, modal amplitude coherence ang tawag diyan. The closer to 1 it is, okay, the higher is the possibility that what you're getting is a mode, okay, or of frequency or natural frequency of the structure, no? Kaya chine-check yan, no? So ito yung mga frequencies na nakuha niya sa consequence. And then there's mode 1, mode 2, mode 3. Ito yung next ERA, ito yung FEM. So ito measured from the field, ito measured from the simulation. And this is the percent difference, and you can see it's very small, no? Anong itsura ng mga modes na yan? Mode 1, 2, and 3. Ayan, ang mode 1, 2, and 3. So mode 1 is you're bending about one axis. Okay, pag ganun. Yung mode 2, bending about the other perpendicular axis. And then yung mode 3 is twisting. Okay? Nag-twist yung structure, no? Yung Carilion Tower. Okay? So, summary. Okay? That's it. Fundamentals of structural health monitoring were discussed, including sample applications for the Tatara Bridge, ICE L1 and L2, UPD Carilion Tower, and the natural frequencies were measured on the field to serve as baseline data in the event of damage, and FEM models for 2 and 3, ICE L1 and L2 buildings and UPD Carilion Tower were developed for comparison with measured results and for future investigations and or sensitivity analysis. So these are the references that I use. Thank you very much for your kind attention.
Okay. Are you still there? Thank you, Doc Jaime. I'm still gathering my thoughts. No? Medyo kahit na matanda na tayong engineer, marami pa rin tayong natutunan. Tama-tama pala yung tawag na sa inyo, no? Doktor. Dr. Jaime and Dr. Ferre, para kayong doktor ng building.
Kaso hindi kami pwede magbigay ng reseta.
Hindi, pero ang reseta nyo, it's in the form of corrective actions. Kasi parang nakita ko yung analogy, di ba? Parang yung tao, yung person, kaya nga health monitoring, may analogy, yung tao, mayroon siyang sariling characteristic na tinatawag na pulse, no? Or heartbeat, or what you may call, yung, di ba pag mayroon tayong tinatawag na ECG, tinetest natin, no? Kaya pag may mali, may sakit, pag in-ECG at may ibang mga lumalabas sa resulta, may yun, that is an indication that there is something wrong. Hindi yung basta-basta na lang ooperahin ng doktor, no? So kayo, ang ginagawa nyo, yung building, parang tinitingnan nyo yung kanilang pulso, no? Yung kanyang heartbeat, yung kanyang natural period, yung kanyang ECG, nga. And from there, magkakaroon kayo ng assessment, analysis. Pagkatapos, malalaman natin kung may diferensya and the appropriate correction.
Yeah.
Medyo mabigat, Kaya siguro, hindi ako magtataka kung pagkatapos na mag-graduate ng mga participants natin, maraming magma-master's degree sa ganitong field. Kasi maganda, Parang interesting, no? It's really interesting that we have this technology and we have these programs available. I'm not selling our program, but na-realize ko na, siguro kung bata-bata ako, mag-aaral ako niyan. Pa-retire na tayo, kaya
Pwede pa.
we will leave it to our young engineers, no? Okay, so Yun ang aking parang reaction muna, no? So we go to the question and answers ba, or si Doc Eric, baka mayroon kang comments
Yes,
there?
sir. Thank you po sa mga presentations ulit, Doc Fer, tsaka Sir Jaime. Remind ko lang po muna ulit yung mga audience na pag meron po kayong tanong, ano na lang po sa chat box or sa Facebook and YouTube na mga platforms. Meron actually tayong questions na dito. If I may, isang question na tinanong ni Sir Joaquin Ramos over Zoom. Siguro this is addressed to Sir Jaime. So yung tanong po is, how important is it to filter out noise from the acceleration data from buildings, and what would be the best way?
Tawag dito, that's a very good question. No, noise, okay? Yung noise, ang definition natin ng noise, it's unwanted data or unwanted vibration from the environment. That's noise. That's what we consider noise. Ngayon, merong times na yung noise could be bigger than the vibration that you want to measure. Yun yung problem. Okay? Kasi for example, if you have yung free vibration time history, the free vibration time history, malaki yun eh. Compared to the noise, kuha agad yun. Okay? Madali lang ma-identify yung free vibration history sa consequence. Pero tawag dito, kapag yung cases na malaki yung noise compared to the vibration that you are trying to measure, okay? Dapat ma-filter out mo yung noise. Okay? Para makuha mo yung tamang vibration na gusto mong ma-measure, no? How do you do that? Yung ginagamit namin dati, mga digital filters, no? So using MATLAB, okay? So we have the raw data. Okay, we have an idea what are the frequencies, parang yung tawag dito, yung ano ba yan, range of frequencies ng noise. Okay, so gagamit kami ng filter, digital filter, to be able to isolate, okay, or remove that noise, no? Or kung alam namin yung frequency tawag dito, nung vibration na gusto namin, gagamit kami ng filter ng noise para ma-capture lang yung part na yon. Okay, parang gano'n ang ginagawa namin approach. So, true, no? You have to remove the noise vibration data in order to be able to come up with good results. Okay. So, thank you for that question.
Yeah, thank you, sir.
Questions tayo dito sa chat, marami-rami na rin, Eric. Do we read them chronologically as they appeared, or is there any? Ayun pala yan, naka-flash sa screen.
So ito po yung next tanong. This may be, kapag po ba magkalayo ang center of rigidity and center of mass ng structure, recommended po ba na baguhin ang dimensions ng column para magdikit po yung dalawa para maiwasan po ang torsional mode? Ano po yung possible na effect sa structure?
Eccentricity topic nito, ano?
Baka si Sir Hermar ang makakasagot niyan.
Sige. Kung problem ng eccentricity, pwedeng i-modify natin yung dimensions ng structural members, or baka better din magdagdag tayo ng structural elements para mas mabalanse siya, para ma-minimize yung torsion. Mas maglapit yung center of rigidity sa center of mass. It's better na hindi magkalayo yung center of rigidity sa center of mass para lumiit yung torsional effect.
Any other question or may follow-up question ba doon?
So yung tanong kung pwedeng baguhin yung dimensions ng columns, at pwede rin naman magdagdag ng structural members para ma-change yung stiffness.
Okay, yung susunod na question, may comparison na po ba yung experimental results discussed by Prof. Hernandez versus sa codes discussed by Prof. Hermar?
Anong kino-compare na sinasabi? Experimental results?
I think the question is because nag-mention kasi na, well, yung discussion ni Doc Jaime sa mga experimental,
yung frequencies.
Tapos yung kay Doc Hermar kasi nagbanggit siya ng I think in his introduction na yung sa codes, di ba, na he was a part of the team that reviewed the code. So siguro gustong i-connect, no, kung anong meron na sa code that take advantage of this knowledge, of this information. I think that's the question, no. Meron na bang parang connection, no? Meron ng yun nga, relevant work towards
there have been many studies already measuring vibration of structures and then coming up with the fundamental frequency of vibration. Okay, meron ng mga study na ganyan, actually using ambient vibration. Okay, kasi nga pagka malaking structure na talagang hindi mo mapapa-excite yan, no? So kahit na hatawin mo yan, hindi magbabibrate na gano'ng kalakas yan. So kailangan na ambient vibration yung ginagamit. So maraming nang gumawa ng ganyan, okay? Pero na-realize is for a structure unique. Okay? Kasi iba-iba yung properties niya, iba stiffness, iba yung material. Although close yung mga values, okay, ng mga frequencies, unique sila. So, tawag dito, kaya nga yung sinasabi na if you have a model of the structure, if fine-tune mo siya, yung model mo, based on what you measured on the field. And that means changing the properties, no? Adjusting the properties of your structure, of your scale model, not scale model, of your simulation model, para ma-capture mo yung nandoon sa actual. Tapos yung model mo na yun, then that can be used for structural analysis. No? So, may comparisons, okay? Pero yun nga, very unique. Okay? Tawag dito. Hindi ko alam kung si Sir Hermar merong alam na specific na ginawa. Okay? Alam ko merong isang building na pinag-aralan dati, ginawang masters dito sa Institute of Civil Engineering. Okay? Tawag dito. And yun nga. Basically lang determine yung natural frequency of vibration ng structure, not really to say kung tama ba yung estimate or what, no? Pero to determine the actual natural frequencies.
I think ang related question siguro doon na is there anything in the code that mentions about yung ganong klaseng mga analysis sa health monitoring? Kasi of course we know the code is basically how to design a building, particularly new buildings, no? Although meron din mga mention about retrofitting, but specifically sa health monitoring, do we have something, Doc Fer, sa code mentioning about yun nga, parang kailangan ba na every month or that's too close, every year minomonitor, something like that, para sa doktor, sa tao, na every year may executive check-up, parang gano'n, di ba? Is there anything?
Sa California, yung after the earthquake, so meron silang mga, of course, yung basis ng design nila, yung frequency, meron silang as built plan, meron silang frequency or period as design, and then after the earthquake, nag-measure sila ng mga vibration frequency, and doon nila nakita nag-change yung frequency, so doon nila nalaman na nagkaroon ng mga damage sa structure. Visually, hindi nila nakita na yung mga damage, pero upon yung checking nung frequency, nung vibration frequency, nakita nila yung check upon further investigation. Doon nila nakita yun. So usually, I guess after a major event, doon kailangan gumawa. And for baseline, baseline determination ng frequency, kailangan din siguro makuha yung natural frequency.
Then siguro ang question kung is there any plan to parang codify or put into the code some kind of regular maintenance or monitoring rather, parang ganun. Siguro in the future, no, we can recommend to ASEP na magkaroon ng parang ganyang klaseng diagnostics or monitoring nga, no? To take advantage of this knowledge. Meron pa bang question? Sige.
Sa ngayon, ang requirement sa code yung paglalagay ng pag-install ng accelerometer. Merong ganoong requirement for some buildings.
Actually, it's already a must. Pero ang ano doon is yung accelerometers na yon are for earthquake engineering monitoring, not I mean earthquake monitoring, not for structural health monitoring.
For structural health.
So pero nga pwedeng may application sa structural health monitoring, you know, you'll be able to measure natural frequencies using those sensors. So pwede rin.
Okay, so may question pa ba?
Yeah,
Meron pa eh. Sige.
Maraming tanong actually, sir, and thank you.
Very interesting kasi ang topic natin, although medyo lumalampas na tayo sa I think they don't mind staying because of the topic, ano. Sige, let's plus the other questions kung meron pa. Okay, let me read it na lang, ano. What are the existing engineering problems po na kino-consider as a challenge sa pag-practice ng structural health monitoring? Okay, Jaime ito.
Okay. Yung mga structures, especially overseas, no, na talagang linalagyan nila ng sensors, as in deliberately, ang daming sensors, no? I mean, hindi lang accelerometers, meron pang mga strain gauges everywhere, no? Yun yung mga important structures that they built, no? Ano yung mga important structure? For example, yung Tatara Bridge, that cable stayed bridges, no? Ang dami ng sensors nakakalat doon sa buong structure. So ang dami nilang data na nakukuha. Tawag dito. Ang alam ko yung Burj Khalifa, for example. Okay? Meron silang mga tawag dito sensors na built into the structure, no? To monitor yung behavior ng structure over time, no? So yun, mga important structures yun ang linalagyan nila kasi expensive to maintain, kasi nga totoo naman ang mahal ng capital to start that building, or that structure, to build that structure. So yung in that sense, yung maintenance, okay, maliit lang siya, yung monitoring na yun, yung gastos, kahit na mahal for us, sa kanila mura lang yun relatively, kasi ang mahal-mahal ng structure na yun ang tinayo as a consequence. So it's to their advantage that they monitor and make sure that the structure remains healthy, remains safe, okay, over time. So yung cost is a challenge. Okay, the cost is a challenge. Tawag dito. Tapos tawag dito. Tingnan, sabi ko kanina, you need to be able to find a damage sensitive feature, di ba? And sinasabi nga ng marami, natural frequency could be used. Now, you could actually come up with other damage sensitive features for a structure, for a specific structure, no? Pwede kasing iba yung damage sensitive feature na pwedeng gamitin to detect damage. It could be a variant, for example, of the natural frequency mode shapes. It could be a variant of that. No? It could be derivatives of that. So ako, for example, no, when I did my PhD in Japan, I was trying to detect damage on piles. Okay? Pero ang mini-monitor ko, ang mini-measure ko yung vibration, yung upper structure, yung exposed, no? Kasi yun lang naman yung makukuha mo eh. Yun lang naman yung makikita mo. So, tawag dito. And I'm using still vibration, no? So I measure the vibration of the structure. Then based on the undamaged and damaged pile cases, okay, I was able to determine na, okay, up to a certain amount of damage, I'm able to detect it. Pero merong certain amount na hindi ko ma-detect, no? Because of the noise, okay, because of different possible different causes of the changes in the vibration. So, may ganun, no, ng mga considerations. Pero you're not limited nga to just tawag dito, you're not limited to vibration, no? Not limited to natural frequency. I mentioned about Doc Oka kanina, no? Antonio. Doc Antonio was trying to determine possible cracking in beams, that have ano ba yung nanoparticles added to the mix, no? To the mix of the cement. Okay? So yung nanoparticles, okay, nagko-conduct kasi ng electricity. So tawag dito, the idea is, okay, again, you apply a current on one side. If the current goes through completely, edi walang damage. Pero kung hindi mo ma-detect at the other end, teka muna, may crack. And therefore, wala kang may-measure na current on the other side, no, as a consequence. So, maraming possibilities, but these are all challenges, no? Determining what damage sensitive feature to use, no, in your structural health monitoring. I hope that answers the question.
I think to summarize the problem, the question, no, I don't know if this is my interpretation. Is it just a matter of cost, Jaime?
Tawag dito.
Kasi the technology is there, right?
Technology is there.
So it's a matter of cost.
Yes.
Do we have the resources to do that? If you have, then okay na, pwede nang gawin yung sinasabi natin because it exists in Japan, in the US, no? So parang summary na question, what are the existing problems in the practice of structural health monitoring? So to me, lumalabas, the technology is there, the challenge is it might be expensive. Parang di ba?
Oo, malaking challenge 'yun. For first world countries, hindi ganoon kalaki ang no. And plus we have to note that first world countries, they're so into extending the life of their existing infrastructure. Kasi natayo na nila yung kailangan nila ng mga infrastructure. Tayo, nagtatayo pa tayo. We're still building our infrastructure. So sila ang stage nila is okay, ayaw natin masira agad. We want to be able to extend the life of the structure so that we can use them, no? Continue to use them. Otherwise, they have to replace them. Malaking gastos na naman yun. So yung kaya monitoring is very important to them, no? Unlike tayo, we're still building So tayo, build. So I do not know kung gaano ka sensitive na ngayon yung industry sa health monitoring ng structures.
Okay.
Maraming salamat, sir. Actually, marami pa tayong questions dito sa chat. No? Pero we're down, siguro because of time, so 2 questions na lang muna. So I hope we can answer some of the other questions offline, no? Kung okay lang po sa mga speakers natin para masagot man lang yung mga ibang katanungan. So ito po yung last 2 questions. Yung una, how well prepared are the infrastructure in NCR in regard to the big one? Are there any major structures that need immediate structural monitoring in the NCR? Medyo mahirap na tanong, but any thoughts regarding this matter? At yung pangalawa, alin ba ang mas sumisira sa building, yung frequency ng vibration or yung amplitude ng vibration?
I will leave it to Sir Germar to answer these 2 questions. I'm sure kaya
Okay. Sa infrastructure, actually may ongoing may project DPWH sa public buildings na to assess and if necessary retrofit yung mga public buildings, initially mga school buildings and some government buildings. Ay sa mga other infrastructure like bridges, meron ding ongoing na program ang government. So maybe hindi lang structural monitoring pero evaluation and retrofitting actually. Alin ang mas sumisira sa building, frequency of vibration o yung amplitude of vibration? I think pareho. Kasi pag malapit yung frequency ng vibration dun sa frequency ng vibration din ng exciting force ng earthquake, makikita natin na mas nagkakaroon ng resonance at nakakasira yon. Kahit na like yung sa example nung sa Mexico, maliit lang yung TGA pero still nag-cause ng much damage. Pero pwede rin na kung malaki yung amplitude kahit siya maliit yung rather, malaki yung amplitude, ibig sabihin malaki yung acceleration kahit na maigsi yung vibration, pwede rin siya maka-cause ng damage dun sa structure. So I guess the answer is both.
And if I may add, kung malaki na yung amplitude, tapos yung frequency malapit pa, edi mas grabe.
Lalong mas
So yung dalawang yan, magkaano yan eh. Oo. So wag natin pabayaan na malapit yung natural frequency ng building sa expected natural frequency of vibration of the incoming earthquake. Okay. Sige. Do we have another one?
Ayun na po, last na sir. Baka offline na po yung iba.
Sige.
And,
sigurong tanong, pwede naman sigurong isagutin yan by email, ano?
Yes,
or unless they want to extend the discussion after everything is yung kasi unahin muna natin yung mga dapat na yung mga pa yung nandito, may mga yung awarding of certificate, gano'n, tapos yung sige, yung tapusin na muna natin siguro yan. Okay?
Yes sir. So maraming salamat po ulit sa mga nagtanong. So meron po tayong as announced kanina, meron po tayong mga winners. 5 of you guys who ask questions will receive meron po kayong prize, no? So ito po yung mga winners. Si Jumar Sakyan, Rich Kahayon, Martin Calao, Paul Paglinawan, and Oliver Gonzalez. So please send your GCash account, name, school, email to this email, ce4lenny@gmail.com. Congratulations, guys. So so we will be giving this certificate to our speakers. So I will just read. This is our certificate of appreciation. This is presented to the speakers for sharing their time and expertise in the Civil Engineering Webtalk number 8, Ramdam ko ang Pulso at Kalusugan mo building vibration and ground motion. This is given on this day, signed by Dr. Andres Oreta and Engineer Emmanuel Yanes.
Thank you.
So siguro to give a synthesis and of this webinar, give the floor to Sir Jun.
Okay, so synthesize to parang concluding remarks, nga, no? So una, salamat sa dalawang ating speakers sa mga natutunan natin na informasyon, no? Although konti yung oras, nabuksan ng konti kahit paano yung ating awareness, no, that such things exist, no? Sa pagdisenyo ng gusali, nalaman natin na ito dapat nating alamin ng kalusugan at pulsuhan ng epekto ng pagyanig na lindol o iba't ibang puwersa. Sa pamahalaan, para i-connecta natin sa pamahalaan, ay dapat masusing pinag-aaralan ng iba't ibang hamon na makakaapekto sa mahusay at matibay na pamamalakad ng gobyerno. Dapat ay pinupulsuhan ng mga nasa tungkulan ang kalagayan ng bansa para malaman ang karapat-dapat na disenyo upang matugunan ang pangangailangan ng bayan. Kaya tayo namang mga mamamayan, dapat din nating pulsuhan ang mga nagnanais na mamuno sa atin, pumili ng mga leader na may matibay at na pundasyon at pag-unawa sa matapat na pamamahala. Muli, salamat sa ating speaker sa kanilang ibinahaging kaalaman ukol sa kalusugan ng mga buildings. At sa puntong ito ay nais kong ibahagi at pakinggan natin ang mensahe ng ating butihing Vice President, si Vice President Lenny Robredo, na may mensahe para sa mga engineers, lalo na itong mga kabataang engineers. Okay, so pakinggan po natin ito.
Naging malinaw sa amin, kapag kabataan ng katuwang, laging may maiaambag na bago. Buong-buo ibinibigay ang sarili at laging ibinubuhos ang lahat ng energy sa gawain. As civil engineers, malalim ang gagampanan ninyong tungkulin sa pagpanday ng mundong pinapangarap natin. Engineers find harmony in the moving parts and make sure that every component allows the organic whole to function and work well. You will not only plan, design, and oversee the construction of buildings and infrastructures. In doing so, you will reflect what we value, whom we care for, and what we dream of. You will shape the way we experience things, from roads, railways, and bridges, to harbors, dams, and irrigation systems. Your task is not simply to work on blueprints of metal, wood, and stone. The structures you build will form, in literal and metaphorical concrete, the very backbone of our nation. Ang mensahe ko ngayon sa inyo, pakinggan ang kwento ng mga komunidad. Magbabad sa pinagdaraanan nila. Bitbitin ang mga dalahing bitbit nila. Gawin ang kayang gawin para ibsan ang pagdurusa. And as you make each other's dreams and battles your own, remind one another of the good you are capable of doing. Empower and draw strength from this community and pave the way for even more to follow. Ngayon, higit kailanman, dahil sa inyo, mas lumalakas ang loob namin. Walang pandemyang hindi kayang sugpuin. Walang pagsubok na hindi kayang lampasan kung paiiralan natin ang malasakit at pagtutulungan. Kaya tuloy lang, padayon lang. Lagi ninyong tatandaan, hindi kayo mga bata lang. Mga Pilipino kayong may kakayahan at lakas na gumawa ng mas patas at mas makataong mundo para sa inyong mga sarili at para sa bawat Pilipino. Maraming salamat, mabuhay kayong lahat.